This is strengthening the chain of trust. I'm Kevin Lane with Hewlett Packard, along with Jeff from Inside Software. I'll start off giving a background of UEFI and Secure Boot, and then Jeff will kind of dive us deep into securing that chain. So, quick intro to UEFI, some of the myths of UEFI, how to use Linux with Secure Boot, and then continuing the chain of trust. So the UEFI specification, what exactly is UEFI? And this is from the UEFI Forum. And it defines a PC operating system and platform firmware interface. And as was discussed in the session earlier, this is the successor or replacing PC BIOS, which have been around for ages, as long as some of us in this room. And it was showing its age very rapidly as new technology came about. You'll find that almost all implementations of UEFI support BIOS legacy mode. If you press escape or F2 or whatever function key will get you into your firmware when you boot up, you may see that BIOS legacy mode switch to turn that on and off. UEFI consists of platform data tables, boot, and runtime service codes. And I'll talk a little bit more about that later. It supports remote diagnostics and repair without booting an operating system. And it standardizes booting of operating systems and running pre-boot applications. And it was evolved from Intel's EFI specification. Intel came out with that, the extensible firmware interface. They developed that for use with the Itanium chip. At the time, BIOS just would not work with the Itanium architecture. EFI was deprecated by UEFI in 2005 and is currently managed by the UEFI Forum. Milestones for UEFI, the mid-90s was the first Intel HP Itanium release, and as I stated, this was due to BIOS limitations, 16-bit processor mode, a meg of addressable address space, and the PCAT hardware. It just did not meet the needs of the larger server platforms like the Superdome. 1998, EFI created the Intel Boot Initiative. In 2005, EFI transformed into UEFI. 2007, Specification 2.1 was released, which included cryptography, network authentication, user interface, and architecture. 2008, that's a major milestone. Secure Boot was added, and we'll discuss that a little bit more. And just last year, Specification 2.4 was released, and that was updated again to 2.4b just recently. So Secure Boot, the bane of most Linux users when it was first announced. It's the security protocol component of UEFI. It secures the boot process by preventing loading of drivers or operating systems. And here's the key point. It prohibits rootkits. That's the main reason Secure Boot came about. And Microsoft caught a lot of bad press about Secure Boot, mainly because they were the only ones that had the keys. But they actually did a pretty good thing here. Secure Boot protects your PC from rootkits. Rootkits get injected at boot time. They're very hard to detect, and they can wreak havoc with malware and viruses. So by securing the boot process, and if you think back to when Secure Boot came about, as much as we like to not acknowledge it, Microsoft is the prevalent desktop operating system, and it was the biggest target for rootkits. We didn't see that much of it in Linux, so that just compounded our angst against the Secure Boot issue that Microsoft came out with. So with Windows 8 and 8.1, Secure Boot is mandatory, has to be implemented. The keys were developed by Microsoft and embedded into the UEFI firmware, and there was a discussion earlier about other keys. And again, it's being looked at, but you have to remember we're dealing with firmware, and there's only so much room to keep putting things into it. And it is the UEFI feature causing the most Linux boot issues. People can't get their system to boot Linux with Secure Boot turned on. And if your Linux distribution isn't UEFI aware, you're not even going to see it in the boot menu. Myth number one, I can't install Linux on a UEFI computer. UEFI will not prohibit you from installing Linux or any other supported operating system. It may make it difficult to install anything other than Windows 8 if you've got Secure Boot enabled, but it doesn't make it impossible. And then some PC manufacturers also allow legacy mode that'll emulate a PC BIOS, as well as giving you the option to just turn off Secure Boot. Myth number two, Linux will not work with Secure Boot. Again, it can always be disabled. Just turn it off. You can install Linux or anything else you want that your hardware will support. Although most of your newer Linux distros, and especially the major Linux distributions such as Red Hat and SUSE, Ubuntu, they ship with support for Secure Boot in one form or another. So there really aren't any issues if you're staying with a mainstream distro. And then myth number three, TPM. Got to have TPM to do Secure Boot. That's not required either. TPM is just another layer of security. You'll find TPM, the Trusted Platform Module, is utilized a lot when you want to encrypt your hard drive, as it allows a hardware encryption layer versus software. It's not implemented by every hardware manufacturer. A lot of them do have systems with TPM modules on them. TPM is not required to be used. And as I stated, it's a hardware chip. It has an API layer. So it does, since it is hardware, it allows hardware level access. What can I do with UEFI? There is a UEFI shell, which, like any other shell in Linux, you can use to peruse the UEFI file system. You can look at the driver tree. You have a shell. You can do shell-type functions with it. You can look at the firmware, a memory map. You can modify the boot manager, which is different than a boot loader. You can run partition programs, load UEFI drivers, unload. You can edit text files. It's really very powerful, as in most shells are. There's also a UEFI toolkit, and you can access that through Intel. Intel also has all the information on driver development for UEFI. And there are programmable boot options, and that implementation depends on your hardware vendor, what they code into their firmware to allow you to do. There's also a tool called Refind, which is a boot manager. Not a bootloader. You still have to have a bootloader like Grub 2 or the Windows bootloader. Boot manager, most BIOS or firmware implementations will include a pretty rudimentary boot manager that you can create boot entries, remove, or edit. Refind gives you a nice graphical little interface to it, a little more easy to manage. As you can see here, you've got EFI shell, Ubuntu, Windows, various other operating systems that will support through a bootloader. How do I get Linux to work with Secure Boot? Well, one way is just to disable it. Turn Secure Boot off. Well, that's bad mojo. You're turning off your security. You're just opening yourself up to the possibility of a rootkit. And again, most major Linux distributions support Secure Boot. And you can add a signing key to the firmware, and Jeff will talk about some of the ways you can do that. Which brings us to the chain of trust, and Jeff.
Hi, thanks. Our intention in this second part is to speak to the community that is trying to systematically design and maintain a secure environment. So the end user who buys a computer and throws Linux on it, hopefully he's going to get taken care of by the mechanisms that we talked about here. And you'll see that falls out. But if you're a large installation with a lot of Linux machines, you end up having some very special problems. What are we trying to accomplish here? Well, the jargon in the security community would be a root of trust and then a chain of trust that builds on top of it. In other words, a set of steps where we can attest that we're secure at each stage. Now, in today's typical enterprise server, the root of trust would be, well, the UEFI firmware. However, increasingly, there are steps before the UEFI firmware which check the UEFI firmware before dispatching it, provided by the hardware manufacturer. So there's an even deeper root of trust off to the left there somewhere, which is the hardware. But let's stick with the firmware. The firmware needs to check the next step in the boot process. We'll call this the UEFI preloader. And the preloader then is going to check and verify the Linux loader. The Linux loader is going to check the Linux kernel. And the Linux kernel is going to check what comes next, which would be device drivers, applications. And the mechanism for doing these checks is typically a mechanism of what we call signing. In other words, the manufacturer of the software, the creator of the software, will attach an encrypted certificate to the software, which is tamper-proof. And by checking the certificate of the next stage, you're able to confirm that it has not been altered in a malicious way since it left the creator. So if you trust the creator, then you can trust the software is what he prepared for you. So we're starting out in the firmware. The way that the Linux community decided to implement this was through the creation of what we would call a preloader or a shim. And the rationale for this is that the next stage, the OS bootloader, changes rather frequently. So we needed something as a root of the Linux boot process that could be relatively stable and unchanging. And so shim binary, the shim.efi, it's an EFI executable, can be distributed signed by the Microsoft CA, which we talked about earlier. And so someone can create a shim of their own for their company, submit it to Microsoft, the signing is free. There's a certain amount of verification that goes on to make sure that there's nothing malicious. It's also possible for a specific OEM or a specific dedicated system to sign their own shim and provision that key into the firmware. When I say key, I'm talking about the public certificate, public key certificate, which is used to decrypt and validate the signing certificate attached to the software. So we continue with the boot. Shim is going to verify the next bootloader, which in this example is grub2. And grub2 uses a service provided by shim to cryptographically verify the next stage in the boot process. So grub x64.efi in this case, can be signed by a distro created key. This is a very common strategy. Or it could be signed by a user enrolled key, an administrator enrolled key. And this is what we'll call the machine owner key, the MOKE. So if we take the most common example, simplified, we'll see that doing a secure boot with a standard Linux distribution, Red Hat, SUSE, Fedora, and Ubuntu, we're going to go through two phases. Three phases really. First we're going to be in the security domain of the system firmware, the root of trust. The system firmware has a copy of the UEFI CA public key, and it uses it to verify the preloader, which is shim.efi in our example. And it has built into it the distro key, which it uses to verify the Linux loader. And the Linux loader uses to verify the kernel. So we can model this as a three-stage, right? But this is great. It has a lot of advantages. It works right out of the box with standard hardware. And since there's no locally generated keys, there's no need to set up an infrastructure to prepare and manage the local keys. The disadvantage is, though, that you don't own that shim.efi. It's not practical to then rebuild grub Linux or the drivers. So if your organization is comfortable and has as a policy, you're going to use the distro bootloader, you're going to use the Linux kernel, this is a very simple and effective strategy for you. But it doesn't always work out that way. For one reason or another, an installation might need to rebuild something, to add customizations, variations from the basic distro releases. So this is where we get to MOKE, machine owner key. So it's in the functionality of the shim, there is a capability for it to load into itself a key that was provisioned to the platform earlier. And then that key, the machine owner key, can be used to verify the Linux loader and the Linux kernel. The way this is done is that UEFI provides a certain amount of storage in terms of its system flash, and it's possible to store your key into the system flash in such a way that it's invisible after the transition to the OS. So if the system firmware is trusted, and the preloader is trusted, and the Linux loader is trusted, no untrusted code has run that is able to see and tamper with the MOK key. So if you need to put your organization on this path, your data center, your company, first thing you got to think through is, how am I going to create and keep safe the signing, the private signing part of my MOK key? And so this, depending on the risks involved, it might involve purchase of secure key storage and signing equipment. We certainly recommend that. It's not the kind of thing you want to put on a USB key and have in Jim's drawer, right? You really want to think through, how do I protect this vital link in my system security? And then the second thing you want to do is provision the public part of the key to the system. And if you take the typical distribution, take Red Hat for example, the steps would be to run an open source utility, MOK util, which is going to request the install. And then there's a second piece of functionality called MOK Manager, which will use the UEFI functions to install the requested key. And then in your corporate infrastructure, somewhere you have that private key, which you can then use to sign anything that needs to be rebuilt and is no longer signed by the distribution. It does require a little bit of hands-on configuration for every system, but it's relatively painless. There's no BIOS menus involved. It's what I would say is painless. So a site policy can be constructed that is very flexible to meet your needs. Now here I have a typical site policy. The shim, in this particular site, we're just using the standard shim provided by the distribution that's signed by the Microsoft CAQ. Firmware recognizes it and trusts it. And at this point in time, we're happy with Grub, but we didn't need to rebuild that. We did need to rebuild the Linux kernel to put some kind of a new kernel change in the kernel build options, an embedded driver, something of that sort. And so we were needing to re-sign that kernel with the MOK private key. You know, there's probably 600 drivers and 599 of them we're completely happy with, so we just keep those with the distro signing, but we did need to rebuild one driver. So we rebuilt it and we re-signed it. So it's not like you have to go out and sign all 600 drivers and maintain those against every time there's a release in a driver. The trust environment is cumulative. So at this stage, I thought I had another slide in there. I must have cut it. All right. The point I want to make here is that the keys accumulate on the key ring as the boot process proceeds. We trust the UEFI CA, that goes into the key ring. We trust the distro key, we purchase the distribution, we trust their key, that goes into the key ring. And then we found the MOK key during the execution of shim.UEFI. We added that to the key ring. So when we get to these drivers, we get to these Linux kernel, it looks to see, do I have anything that matches what this was signed with? So it's not an all or nothing situation.
So Jeff, it's probably worthwhile pointing out that key ring is volatile, so it disappears and then reboot.
Exactly. The key ring is created as the James made the point, the key ring is created as the boot proceeds. And so the next boot, if you change your MOK key, then you're going to have a totally different key. You're going to have a different member on that. It's not a permanent trust. It is, I think that model is probably very convenient for a lot of enterprises. It provides strong security. But there are those enterprises which want to take total control and only run those binaries that they themselves have inspected, built, signed. You know, it comes to mind, you know, government, perhaps banks. It depends on the local policy. So UEFI does allow a site to take total control of and have the machine owner key be the root key. The machine owner key needs to be installed into the system firmware, replacing the UEFI CA key. And then shim.EFI needs to be rebuilt from open source, inspected, tested, signed. The loader the same, the kernel, the drivers. And so this one key, or it can indeed be several keys if that's more convenient to you. This one key then is the only thing that will allow software to run. How is this done? Well, I have to warn you, it's a fairly high-touch expedition into the bowels of Secure Boot. But for the organization that's motivated, the tools are available on open source. It's called EFI tools. And what this does is you provide it with your list of public keys that you trust. Could be one, could be several. If you're going to use option ROMs from third-party vendors, like, say, an LSI RAID card or an Intel High 10G network card, in this list, you probably want to include the key that signed those option ROMs, and that's probably the Microsoft CA. Unless you have an arrangement with that company such that you can get the binary, re-sign it yourself, and reinstall it. All of this goes into your planning, your policy of what my site is willing to. And you create a custom database in the form of a EFI executable. And now it gets kind of messy. At this point in the evolution of UEFI, for reconfiguration, we rely on a concept called physical presence. That's what we name it. Okay? If there was a API that is scriptable that would allow the security database to be turned upside down, then this API would be an attack vector, a vulnerability. Sure, you could layer on some authentication and so on top of that. And indeed, the UEFI committee is working very hard to figure this out. because these steps of clear firmware, using the BIOS menus, and run the lockdown, these are labor intensive. The exact steps in terms of what arrows to move are different for each system vendor. It's certainly there for the motivated organization. Works. Do we think we can make it better over the next 2 years? Yes, I think stay tuned to this channel. We're going to be proposing more automated methods for organizations to take control. There is a lot of help out there on the internet to help you plan that policy that I talked about and then implement it with the distro of your choice. I thought, the Red Hat System Administrator's Guide was about the best. They obviously put a lot of effort into it. And so that would be a place to start, especially if Red Hat is your distro. Fedora organization has a secure boot guide. It's a little bit incomplete, but gives you some of the basic concepts. SUSE's documentation is great as well. And this is sort of the famous back of the napkin diagram repeated here for how MOK came into being. But we're going to have all of these presentations posted. You can use these links to find more in terms of setting up your policy. And I've listed a couple web books and web blogs which I find helpful to keep up with how the industry is moving and changing. All right. I'm going to, I thought I had a list of what's coming up. No, I guess we didn't do that. It's on the other presentation. I'm going to open the floor to questions and discussions. But rest assured, we have another presentation after lunch. Go ahead, right in the middle.
Is there a requirement for the mock keys to be trusted by whatever you already have in the system?
No, it's cumulative. So this keyring concept, right, accumulates as the boot proceeds, and as a trusted key is added, the next stage will be trusted if it's signed by any of the trusted keys.
Okay, so if I'm adding a new mock key, so it should be trusted by an existing key that's already either in the DB or the mock database. Is that right? I don't get the concept of keys trusting keys. It's a little more complicated than that.
So the concept of keys trusting keys is usually you've got a signing chain. Is that what you're asking about?
Yeah.
So there is no signing chain between the MOK key and any key in the DB because these are a set of keys that we apply trust to, but they don't necessarily have to go back to a certain root of trust.
So this database is defining the root of trust for this machine. Would that be a fair statement?
The union of these keys defines the root of trust, but then it's a multi-rooted tree.
Did everyone hear that? Should I repeat that? It's an important point. In the system firmware, we might have the Microsoft CA key. The preloader loads the local installation key, the mock key. It also contains within itself the distro key, right? The distro key that was built in when the distro was created. So from this point forward, all three of those keys are trusted. They're three separate domains. We trust anyone signed by the firmware keys, the firmware factory keys, right? We trust anyone signed by the distro keys, and we trust any binary that's signed by the MOK key. So it's an expanded security envelope.
nothing prevent us to remove keys from some DBs, so we could
Exactly.
remove the trust of some actors if we don't trust them.
Exactly. In this setting of taking control, right? We didn't talk about it, but you can also revoke in this whole process. But since you're creating the envelope of keys, your revoking is likely to be limited to specific hashes of specific binaries. So let's say, Microsoft has published a revocation of some dozen or so binaries that were originally signed by the UEFI CA, right? And so this is something that can be added if you want to continue to trust the Microsoft CA for the 99% of things that were signed by it. You can also install the revocations. Once again, it's a high-touch process at this time, and working to make it more streamlined.
Yes. What's support for the UEFI for the measured boot that the TPM allows? Do you support that, or how does it work? Do you want to do measured boot?
Yes. Measured boot is an example of defense in depth. Okay? And you can have secure boot with measured boot. You can have measured boot alone without. They're separate features. But they don't depend on each other. Not exactly. And I'll tell you how they do depend. Measured boot is, or trusted boot as defined by the TCG, causes the hash of the steps. We talked about the steps. It's not a signing check. It's the hashes of each step is accumulated as the steps proceed. And then at the end, when you get to the kernel, you have an accumulated hash that you can compare against a golden master hash, right? And this will then give you some confidence that none of the steps before have been compromised. The problem with it has been that it, in practice, is kind of brittle. Let's say that you get an advisory from your system manufacturer about a firmware vulnerability, and you're really on the ball, and you install that firmware update. Well, now your hash is going to change, and you have to reinitialize your trusted boot. So administratively, it has turned out to be somewhat difficult. So one of the things that you can do with trusted boot is you can have your system firmware measure the UEFI Secure Boot components into what's called a PCR. And then your kernel can take that PCR, that hash of the UEFI components, Secure Boot, as a recommendation that Secure Boot was followed on all the steps up to this point. And that's a less brittle implementation of Trusted Boot. Now, Trusted Boot takes cooperation between the firmware, which is making the measurements, and the OS, which is digesting the results and deciding whether to trust the system or not. And then, of course, once you've booted, the TPM can do a lot of other things for you as well. But, does that answer that? It's a pretty complicated subject.
Yeah, do you have support for it in UEFI? Do you support it? The API is supported?
The way that it's implemented is that the TCG itself publishes UEFI protocols to implement Trusted Boot. And this is a case where the UEFI spec has been leveraged by an outside body that says, okay, everything in the UEFI spec, this is how we do it, right? In other words, the two specs are compatible. And so as a firmware vendor, my company will use input from the TCG in the form of the protocols and recommendations of the trusted boot and the TPM protocols, which are used for things like administering and clearing and initializing. And we implement that into the firmware in parallel with the secure boot requirements.
I have two kind of related questions. First, is only a single MOK allowed, or can you have multiple ones? And the related question is there any indication, either during the boot process or once the OS is booted, either visually or queryable or something like this, for which key has signed the loader of the kernel?
Okay. In answer to the first one, that's an implementation question. I will say in the typical implementations that I've looked at, yes, you can have multiple. It is loaded, it shows it here, shim, but it's actually loaded by MOK Manager.
Okay.
Installed by MOK Manager, loaded by shim on the next boot.
Okay. So this brings up the second question. So if somebody sneaks in and adds another MOK that I didn't plan on, how do I know that what I'm booting is or was signed by mine and not by this second one? Is there any way to verify that or notice that?
That's a little too deep into the Linux security model for a firmware guy like me. I'm afraid to say.
But the answer is effectively no, because at some point in the chain of trust process, you assented to putting the key in there, even if someone tricked you to give that assent.
But after that, there's no. I don't ever know which key I'm trusting at that point. It's
There's no
one of the trusted.
There's no log, no.
Well, the keyring actually carries through the boot. You could, in theory, look at the actual binary you booted and see which key it's signed by and verify it against the keyring. But nothing in a secure fashion tells you what that is. So you actually have to go and recheck it.
Okay.
So did everyone hear that? Should I repeat the question? Okay. We'll go on then.
In case your platform is UEFI Secure Boot and UEFI compliant but doesn't have ACPI, what could be the potential problems coming in to suspend, resume, and breaking the chain of trust somehow? Or do you mandate ACPI if you want Secure Boot?
Yeah, the short answer is no. We certainly do not mandate ACPI as no particular. And the longer answer is resume is something, if you're running a secure environment in an enterprise, resume is something you're going to have to look at fairly closely to see whether that particular process on the particular system and CPU that you've chosen, whether that process is secure. Because essentially what happens, if you think about a resume, right? Essentially what happens is that you get a shortcut jump into the memory image. Right? And if you want to take exception for that, as to whether that maintains the security envelope that you've built, that's certainly, as an organization, that's your prerogative to ban resume. Resume does not go through the secure boot steps.
So actually, there's probably some nuance to this. It depends what you suspend and resume. Suspend to RAM effectively involves never really removing yourself from the hardware chain of trust, because it unsuspends from RAM. The only way to subvert that is the way that one of the ads did, where you freeze the computer and you inject stuff. So it's not impossible to subvert. But if you're thinking about suspend and resume to disk, where you'd actually have to sign the suspend image in something and then verify and resume from disk that you have that signed image, there are believe there are people who are thinking about it, but right at the moment, almost all of our laptops suspend to RAM, they don't suspend to disk, so I think it's seen as a use case that perhaps we don't need to bother about so severely at the moment. It will come when we have to worry about KExec, which is one of the ways that you can upgrade kernels and do everything else. So,
Maybe you should introduce yourself.
Okay,
This
sorry.
is my muse. I'm along, and he's my muse.
I'm James Bottomley, so I've worked quite a long time on Secure Boot on behalf of the Linux Foundation. And so the KExec problem, I think one of the KExec guys is actually working on doing signed KExec kernels. And that will transition straight from a Linux kernel to another signed entity. And it probably would do direct execution. It will even bypass the UEFI load image stuff.
That will be extremely impressive.
As I know, KExec API is currently in almost stable stage, or almost is upstream. Currently, there are works on KExec itself.
Yeah, so Mimi just said it was upstreamed in 317, it should be.
Is that the recommended way to run a custom kernel, just KExec it?
I don't think you want to say a recommended way about something we just put upstream, because in Linux we find that improvement of practice follows execution. So if you want to be the early adopter, absolutely.
How are we doing on time?
30 minutes.
Says 5 minutes.
Okay.
Less than 5.
I don't want to keep you from your lunch.
So the question I have is, looking at this from an enterprise view, if I'm a large
Good.
enterprise.
Good, yes.
And I want to make use of this, the question I have is, why don't I have the ability to be the one to choose the trust? Meaning, if I put my MOK in the system firmware, and if there was, say I bought HP, I'm standardized on HP, okay, I buy HP Model A, whatever. Why couldn't HP publish their EFI signed with a X509 cert, and I could take that, verify on my own, okay, this is a legitimate EFI image, I will now sign it with my MOK, and do that with all the individual pieces. Yes, it would be a pain to do this for a whole enterprise, but I'm asking, why does the model have to be that the system, if I'm provisioning the MOK, I want to be the one that says who's trusting, not someone else said they trust it, and I got to trust them that they said they trust it. I want to be the one that has the complete control, to include signing of firmware. The problem is, they would have to release their firmware. Attestation is that the legitimate firmware, and there's out-of-band methods you can do that.
Well, at this time, for most implementations of most system designs today, the firmware itself is not signature checked. This is changing, and increasingly there are opportunities where the hardware, in effect, will check the signing of the firmware. The problem, and the hardware is maintaining via some fuses the public key of the OEM. The fuses are installed at the factory in that design. Okay? So if you buy an HP server today with today's Intel chipset, right, you're trusting the HP firmware because it has mechanisms, hardware mechanisms, that protect its image from alteration. Right? In the future, you will have a double layer, security and depth. You will have hardware mechanisms which protect the firmware image, plus you will have hardware checking of the firmware image before it dispatches. But still, you're going to be trusting HP, ultimately, in this case. Because unless you're going to get the chips and blow the fuses yourself, which some manufacturer may offer you, a virgin board, and you blow your own key into it. right? That's not going to be the typical case. The typical case is you're going to trust the manufacturer of your system, you're going to trust the firmware, and you're going to take a hard look at that manufacturer's practices, methodologies, before you make that trust decision. In the back.
So, your design that you were just describing is what we're actually planning to do at the OS level. And we want to have the mock key be used to sign to sign other keys that are loaded onto the IMA key ring. And only those keys that are signed by the mock key will then be used to appraise all other software that's being executed or however your policy is defined. So yes, that is what we're doing at the OS level. And in terms of firmware measurement, we just upstreamed, and that's also going into 317, a firmware load that when you load the firmware, that there's an app, a new security hub, and that security hub, depending on what you want to do, different Macs will do different things, and in different places, I believe. Well, I won't speak for him, but I believe that they're just verifying that it's coming from their read-only place.
Mm-hmm.
In the IMA situation, we want to measure it and we want to appraise it. So we do want manufacturers to start signing so that we can start appraising it. And the measurement list all the way up is what we would also like to see.
And that is definitely progress, and it definitely will protect against a variety of threats. But unfortunately, if during the process of getting to that checking, you've run untrusted code somewhere along the line, then you have to have in the back of your mind, did that untrusted code fake the measurements somehow? Fake the signing, whatever, through some trick. So it's really more intended, I think, to say, to give you some reliability that the system firmware is an appropriate version, an appropriate vintage, and that it has all the latest security fixes. We're out of time, and they have your lunch. I'll be here. The rest of the UEFI team will be here.